So today we are going to be talking about the basic equation of statics from the differential volume and then an applied force, and then we're going to be talking about the density in terms of the ideal gas law. So we are going to start out by talking about the equation that everyone has seen before. So it's pressure equals rho GH. So we have pressure equal to the density times the force from gravity times the height. So if we were to look at a situation, say we have a little pool of water here. So the pressure outside of the water would be our pressure initial, and that is 10 to the 5th pascals. And then if we had someone that was under here floating around in the water, our height in this equation would be from the surface of the water to the top of his head. And then the pressure that we're looking for would be the pressure in here. So the pressure in here would be equal to pressure initial plus rho GH. So our density would be the density of water. Our height is right there, and then the gravity force would still be the same. So if we were to start talking about the differential volume of a system, if we draw a cube here, oh, that's a little small, hold on. So if we were to draw a cube, that was terrible. So let's draw a cube here. All right, so if we're looking at our cube, we are going to say that this length here is dz, and then the top surface is going to have an area of A. And if we were to look at a point down here, let's call this Z. That would be called Z, and then if we were to look at a point up here, this would be Z plus dz, because we have this length right here being equal to dz, so we would start at Z, and if we're looking at the point up here, we would go from Z all the way up dz, so we have to add dz. Next, we are going to look at an applied force. So the applied force would be equal to the mass times the acceleration, and it would all be equal to 0. So if we have here our acceleration is equal to 0, so that means that our net force would also be equal to 0. So now we are going to go back to talking about this situation. So we are actually going to move from our person to our cube, and we are going to say that our cube is all inside of this container that is filled with fluid. So now we can look at the forces that are applied on our cube. We're going to have our force down here pointing upward, and since we have the z direction, or the positive z direction going upward, this force is going to be positive. So it's going to be the pressure of Z times the area of this bottom surface. And we are also going to have a force up here that is pointing down on the cube. Since we have our positive Z direction pointing up and this force is pointing down, this force is going to be negative. So we are going to have the negative of pressure of Z plus dz, since we're looking at this top surface. And this is also going to be multiplied by the area of that top surface. So now we can add together all of our forces, and we're going to have force is equal to PZA minus PZ plus Z, or dz, times A. And we also, another force that is going to be acting on this cube is the gravity force. So gravity is going to come in this way, and that force is going to be the mass times gravity. So we need to add that into our equation, since that is a force acting on our cube, and it is going to also it is going to contradict this z direction, so it's going to be subtracted. So we're going to subtract mg, and all of this has to be equal to 0. So now if we think about this in terms of, pressure, we can have mass is equal to rho times volume. But also, if we think about this, we could have volume is equal to the area of this top surface times dz, which is that last length of our sides. So if we were to plug in for our new m and our new v, we would have pza minus pz plus dz times a minus a times dz. We are going to have the density rho. We're getting a little messy here. We're going to have rho times area times dz is all equal to 0. We forgot gravity. Times gravity equal to 0. So now if we do a little bit of algebra, we could have a times pz minus pz plus dz is equal to rho a dz g. So now we want to rearrange this just a little bit. We're going to bring out this negative sign, have negative a is equal to pz plus dz minus pz and all of this is still equal to rho a dz times g. So now if we look, these two a's can cancel out, and then we're going to bring dz over to the other side. So this is going to be divided by dz, so dz isn't on this side anymore. We are also going to bring this negative sign over, so we are going to end up with pz plus dz minus pz all divided by dz, and this is all going to be equal to negative rho gravity. So now one more small thing we can do to this equation to make it a little nicer is if we can see we have the difference between p's up here, so we can have dp divided by dz is all equal to negative rho g. So now if we were to look at this equation when we have a constant density, so if we were to look at this equation down here, when we have a constant density, we could take the integral of both sides, but we're actually going to move dz back over to this side for we have the dz. So we have the derivative of something on this side. So we're going to have the integral of dp is equal to the integral of negative rho g dz. So now if we're looking at these integrals, we are going to make them definite integrals, and we are going to have P1 to P2 on this integral since we're looking at the pressure on this side of the equation. And this side we're going to have Z1 to Z2 since we are looking at the position on this side of the equation. So now evaluating this definite integral, we are going to get P2 minus P1 is equal to negative rho g times Z2 minus Z1. So now we are going to look at this equation when we don't have a constant density. So if we look at the density when we have an ideal gas, we are going to have rho is equal to pressure times the mass over R times the temperature. So if we are to plug this new row in there, we are going to get, we're going to get dP is over dz is equal to negative pressure mass times gravity divided by R times temperature. So this is our basic equation of statics. Now we are going to be looking at an adiabatic reversible process. So if we have this little air bubble, as we go up, the pressure goes down, so the air bubble will expand. Now, if we're talking about heat, the heat is going to be the same inside and outside of our air bubbles. Even, it might change a little bit, but it's not going to change enough to actually matter. So this is what makes it this is what makes it an adiabatic process. Now, if we're starting to talk about the pressure in and the pressure out at each altitude is going to be the same, which makes it reversible. So now we are going to look at the first law of thermodynamics, which is du is equal to dq minus p external times dv. So this dq is equal to 0 since it's an adiabatic process. And in terms of an ideal gas, this P is going to be equal to RT divided by V. Also, in terms of an ideal gas, we will have du is equal to CV times dt. So now our equation is going to be CV is equal to dt, CV dt is equal to negative RT divided by V times dV. So now we are going to take the integral of both sides. C and V are constants in this situation. So we're going to have CV outside of the integral, and then we're going to have the integral from T1 to T2 of T dt divided by T. So we're bringing this T over. And then negative R is also a constant in this situation. So we have negative R times the integral of V1 to V2 of dV divided by V. So now if we evaluate this integral, we will get CV times the natural log of T2 divided by T1. Then we will have it equal to negative R times the natural log of V2 divided by V1. So now we can divide by this CV, and then in terms of natural logs, we can put it in the numerator, meaning we will have T2 divided by T1 is equal to V2 divided by V1 to the power of negative R divided by CV. So now we are going to go back in terms of the ideal gas law, and we are going to find V2 and V1. So V2 would equal, looking at this equation, V2 would equal RT2 divided by P2, and then V1 would be RT1 divided by P1. Now we are going to go and we are going to plug our new values for V into our equation. So we are going to have T2 divided by T1 is equal to V2, which is R2, or RT2 divided by P2. And then we are going to divide by V1. But since we are dividing by a fraction, we can multiply by the reciprocal. So we are going to have P1 divided by RT1. And all of this is going to be to the power of R divided by CV. So now looking at this equation, our R's are going to cancel. So we are going to get T2 over T1 is equal to T2 times P1 divided by P2 times T1, all to the power of R divided by CV. So now we are going to combine these. So we are going to get T2 divided by T1 to the power of 1 plus R over CV is equal to P1 divided by P2, and this is still just to the power of negative R divided by CV. So now if we make the 1 and R over CV have a common denominator, we will get T1 divided by T2 to the power of CV divided by CV plus R over CV. And we are going to have this equal to still just P1 divided by P2 to the negative R over CV. So now we're going to come up here. So this is coming up here. We are going to take both sides of this. So, mess this up. This is T2 over T1. We are going to have T2 over T1 to its power, so CV plus R divided by CV. And we are going to take this to the power of CV over CV plus R. And we are going to set this equal to P1 divided by P2 to its power, which is negative R over CV, to the same power of CV over CV plus R. So this is going to give T2 over T1. So if we look at these exponents, the CV plus R are both going to cancel and the CVs are going to cancel. So T2 divided by T1 does not have a power anymore. And if we look at this one, the CV and the denominator and the CV and the numerator are going to cancel, but we are still going to have P1 over P2 to the negative R divided by CV plus R. So now we have temperature and pressure, or a function of temperature that is related to pressure. Now we can go back and use our equation from part 1 and part 2, and we're going to combine them and compare them. Alright, so here on the board we can see the two equations that we have found in the past two parts of this video. So the one in red is the basic equation of statics that we found in part 1, and then the one in green is the relationship between temperature and pressure that we found in part 2. So if we look at the relationship between temperature and pressure, we can see that the pressure is raised to the power of negative R over CV plus R. So we are going to set a value for that. So we are going to set alpha equal to negative R over CV plus R. So all that is going to do is going to let us write alpha every time instead of writing negative R over CV plus R. So it's just going to make our equations look a little bit nicer and not as messy. So now we're going to solve this equation for T2. So we're going to have T2 is equal to T1 times P1 over P2 to the negative alpha. So now we can see that we have a T and a T in both equations. So we are going to take our T over here and we're going to plug it into this equation. So we are going to get dP over dZ is equal to negative PmG over RT1. So here comes this equation. So we want to divide by the fraction of P1 over P2. So we can actually just multiply by its reciprocal. And since we multiplied by the reciprocal, this alpha is not going to be negative anymore, and it's just going to be plain alpha. So now we are going to multiply in this fraction of pressures. So we are going to have dP over dZ is equal to negative P and then 1 plus alpha in the power, and then mg over RT1 P1 to the power of alpha. So now we can take the derivative of both sides, but we are going to move this P on top over to the other side and this dZ over to the other side. So we are going to end up with P1 plus alpha dP is equal to negative mg over RT1 P1 to the alpha dz. So we are going to take the entire left side to the integral, and then we are just going to take this dz to the integral since this is just a constant. So on the right, we are going to have the integral from z1 to zf, and on the left, we are going to have it from p1 to pf. So all those mean the pressures over here are going to be compared to the z's over here. So the pressure at a certain altitude of z. So it's the pressure at the altitude of z. So now we are going to evaluate these integrals. So over here we are going to have -1 over alpha times p to the negative alpha. And this is going to be evaluated from p1 to pf. And then on this side we are going to still have our same constant, so -mg over r t1 p1 to the power of alpha. And then this is just going to be zf minus z1. So now we can evaluate this side from p1 to pf, and we are just going to get pf to the negative alpha minus p1 to the negative alpha. We are going to bring this -1 over alpha to the other side. So those negative signs are going to cancel out, and we are going to get alpha mg over r t1 p1 to the alpha, and then zf minus z1. So now we are going to move the p1 onto the other side. So we are going to have pf to the negative alpha is equal to p1 to the negative alpha. And since we have negative alpha here and just positive alpha here, we're going to bring that that other p1 up on top, making it a negative alpha. So we're going to have, pull that p1 to the negative alpha out. So we're going to have 1 plus alpha mg over r t1 times zf minus z1. So now we're going to get rid of these negative alpha values. So we're going to take this entire equation to the power of -1 divided by alpha. So we're going to have pf equal to p1 times 1 plus alpha mg over r t1 times zf minus z1. This is all going to be to the -1 over alpha. Now we are going to plug back in our value for alpha back into this equation. So we are going to get pf is equal to p1 times 1 plus. So our value for alpha is -r over cv plus r. So when we plug in, that r is going to cancel with the r on bottom. So we are going to get minus mg over cv plus r times t1 times zf minus z1. Since we have the alpha on the bottom, we can just flip that fraction. So we are going to get this to the power of r over, and we can also get rid of that negative sign since both of them have negatives. We are going to get cv plus r divided by r. So now we can see that we have pf here and p2 here. So we can actually come back up here and plug this equation in for p2. So we are going to get T2 is equal to T1, and we can see that the P1 here and the P1 here would both cancel, and we are going to get 1 minus mg over CV plus R times T1, times ZF minus Z1. And then we can see that we have the negative alpha here And then we have CV plus R here. So those are just going to cancel out, and this is going to be our final equation. So you can see here that we took the basic equation of statics and an equation that was the relationship of temperature to pressure, and we combined them into one equation. Thank you for watching.